As you guys can tell in number 70 as we're grading 6.2, but not all of 6.2, just 70, 71, the only even is 70. They did not even draw the crazy three-dimensional shape even though they could have. They just, yeah. Do you see what they just did? They just did what's on the ground, kind of. They just did like a top-down aerial view. They just looked at the base, which would be the area between the two curves. We have the linear function and we have the parabola function. If you set them equal to each other, or just simplifying, finding the zeros, which are basically the intersections, they were able to find their natural bounds of -1 to 2. Then they have their entire function after. Now, wait a minute, that's not the function. This is the function, right? But what's the cross-sectional slice that's coming up? Square. And what's the area of a square? Side squared or edge squared, or they said base squared, whatever. Side squared, edge squared, base squared. So then they said, oh, hey, top minus bottom is the base, plug it in. So that's squared, and then they went ahead and did, I think they just FOILed it. Because U sub would have been near impossible, because if you chose this to be U, you have no 1 minus 2x on the outside to be your du. So U sub's not going to work. Old-fashioned foiling, then lots of baby power rules, and then plugging in the top minus plugging in the bottom, you get 81/10. Zoom in. Is it a little bit too small? Is that better? Okay. And then as you guys are finishing grading A, B is super similar, except instead of squares, I think they're rectangles with a height of 1. Is that what they said? Height of 1. So then the base, just like the squares, the base is just your top minus bottom. It's just that slice perpendicular to the x, which is why we have all x's in both of these. The base is going to be the top minus bottom. All combined is this expression. The height is just going to be 1, so plug that in the integral. Done, 9/2. Nice thing is, didn't we do squares and rectangles with a base of 1 in our notes? Okay. So you're supposed to be able to kind of just follow that. Yeah, if you don't have your notes, you can look online, right? Or on the video or somewhere else. Okay. So that was, that's section 6.1. That's all of section 6.2 that you were able to do besides number 71. Do you guys have a question on 71? Because you were able to check that one. Are we okay with it? You could have gone further if you wanted, but remember, like I said in homework, we did the section out of order, and so 70, 71, I think it was even back there. Yeah, 70, 71 were the only ones due today. And then the email. No, now you know, it's okay. And so maybe actually today's lesson might make a little more sense as we go to section 6.2b. 71, I mean, you can peek at it fast. I'm not going to leave it up long, though. It's 128/3 and then 32 root 3/3 because that's not a colored pen, Ben. Where's your colored pen? Because you can check this on CalcChat. You can check in the back of the book, etc., etc., etc. But do you guys have any questions on 71? Okay, because in the very beginning of 71, let me take a picture of it real quick, and let's go to the end of section 6.2a. ¿Dónde está? It's a lot like the one that we started on Friday. Oh, is it exactly the same? Okay, so Austin, let's just look here, because it's exactly the same. I didn't realize it was quite that similar. Whoops. They gave you the function x squared plus y squared is 4, which is a circle with a radius of 2, which is how we get the bounds of -2 to 2, just from how big the circle is. But if you were to actually solve for, remember, when we go in terms of dy or in terms of dx, I think the book one was dx, though, wasn't it? Okay, so it's going to look a little differently in that it's going to be in terms of x instead. But all that's going to change is instead of solving for x equals the square root of 4 minus y squared, we'll solve instead for y. But the nice thing is in this one, won't y equal the exact same thing? It'll be 4 minus x squared square rooted, plus or minus though. So the positive square root is the top part, the negative square root is the bottom part. So when we go to subtract top minus bottom, it's going to be a square root, just 4 minus x squared instead, minus the negative square root, which will always end up being double the square root. Does that make sense? So all that changes, it's going to be double just because 1 minus a negative 1, 1 plus 1 is 2. It's going to be double just because it's perpendicular to the x-axis. This would need to be the square root of 4 minus x squared dx, and that's what you see mimicked in. Oh, I just closed it. There we go. That's what you see mimicked here. So they didn't show the whole top minus bottom, but it ends up being top minus bottom in the sense of the positive square root minus the negative square root, and then plug and chug. And then you have to go ahead and solve your integral. Guys, remember, it's not my job necessarily to teach you how to integrate, but if you have questions and get stuck, we can definitely go over it. All right, remember, that's on CalcChat. That's in the back of the book. You were supposed to have already tried it and graded it and come with questions today, right? Isn't that how we've done homework all year? And what month is it? March. So at this point, it's not because you don't know how to do homework, it's because you're choosing not to do it rightly. All right, cool kids. I want us to go ahead and go back into our notes. Because even though we did talk about this kind of crazy one in Austin, it's actually going to hopefully be helpful because we're going to take the same exact function and do a different cross-sectional slice because there's something special with semicircles that I don't want you guys to be without. And then we have an AP multiple choice that has something to do with cross-section. So get out your calculator. There are decimals. This one you wouldn't have to solve the integral by hand. So grab out your calculator. And then we introduce section 6.2b, and Sarah, that's what you were working on, probably kind of hard. Those of you guys that did the email to me with the link, how many of you guys found a video on cross-sectional volumes? Volumes by cross-sections. Okay, I saw a few. And then how many of you guys did volumes with, like, you saw the words or heard the words discs or washers? Okay, and those were the other. You did whatever. The cross sections is what we just finished, which are squares or equilateral triangles or rectangles, and it could be circles or semicircles. You rarely see circles, but you do sometimes see semicircles. But then the next section is going to say, okay, now we have a region that's been spun. So my people that saw discs and washers, this is where we're going to cover the discs and washers at the end of 6.2b, which is really the majority of 6.2 homework. So that's why I kind of added that little extra thing this weekend. And then some of you guys, I haven't read all of your responses because you were turning them in until super late last night. Yeah, it was pretty close. Anyway, it's okay. I got one super early this morning. I bet you can guess which junior did it really early this morning. But anyway, but then coming on back. I'm not sure who all you guys found, and so I don't want to necessarily make a big deal about it right now, but I am going to go ahead and have one of my TAs. I'm going to forward her all the emails, and she's going to compile the links to all the videos so that you guys can see what other people, your classmates, are able to find, maybe beyond the CalcAB or beyond Patrick JMT. Not that those are bad, and maybe you just found those, but I'm hoping you found some extra ones because it'll really help to watch some extra videos. And at this point, guys, you have to choose. You have to choose to finish off calculus strong. It's not easy to finish off calculus strong. We're going to be reviewing soon. Some of you have fallen behind, but I have seen kids in the last month or so before the AP, which is almost where we are, rise from a 1 or 2 to a 3 or 4 or even 5 in that last month. It depends on how you finish. My cross-country track people, how are you always supposed to finish? You're supposed to finish all the way into that finish line, right? When you run the gauntlet, you give it your all because soon the race is going to be over. And if you haven't given it your best, is that a very satisfying race no matter what? No. What you want to be doing is almost falling across that finish line saying, I've left it all on. Ooh, I think that's biblical, isn't it? I've run the race, I've finished the course. Anyway. We're trying to fight the good fight of calculus right now. So, in our notes, let's do a couple more cross-sectionally things, and this is one of them, semicircles. Period 6 was actually able to do a semicircle on Friday. You guys weren't, but that's okay because you were able to do some other basic ones this weekend with squares and rectangles. So, help me out real quick. Perpendicular to the y-axis. Can't we show that, and even in the book, can't we show that by just doing a nice little slice, like a sliver, perpendicular to the y? Is that okay? Okay. That's perpendicular to the y-axis, right? 90-degree angle, right angle? Okay. So this is a sliver perpendicular to the y-axis, and that sliver is going to have some depth, and that depth is going to be dy. So right away, before doing anything else, I know I need this function once again in terms of y, and to get it in terms of y, I solve for x. So without going too crazy, because you guys saw the work on Friday when we did it, it's plus or minus 4 minus y squared. We could say that my base, that's what CalcChat I saw using, or even the answer key, my base is going to be this sliver, and the sliver is right minus left. So then right minus left, does it make sense, my cool kids? I'm just going to go straight to 2 square root of 4 minus y squared. Because this would be positive square root minus negative square root, or think halfway square root of 4 minus y squared minus 0. So once again, we did it the long way on Friday. We're doing the shortcut because we already got there on Friday. This is my function. This is my base. My base in terms of my y variable. But, hold on, what do I need to think about for volume? Forever card. Good, I need to think of an area formula. So, I know v is equal to, we know our circle is negative 2 to 2 because the radii is 2 from this little 4 right here. I need an area formula. Area of a semicircle, what is it? Perfect, 1/2 pi r squared. Now I'm going to write the answer, and I want you guys to think whether or not you would naturally choose this answer, because it's what the AP is going to put almost every time. The answer is going to be 1/8 pi times the integral from negative 2 to 2 of the square root of 4 minus y squared dy. It's a semicircle. It's a half sphere. Well, here's the problem, because they're probably going to ask you to express the answer as an integral. So that's what I'm doing right now. It probably wouldn't be a long answer FRQ problem. Yeah, Sarah. We actually don't need to find the height of the circle, just because any circular shape, whatever is here, is also here. Well, wait a minute. Hold on. What's the radius? Is this whole thing a radius? Exactly. Do you see? Wouldn't a semicircle be what's popping up? And if a semicircle is what's popping up, question, is this, can I make this the radius? And the answer is no. Because what is it instead? Yeah, it's not 1/2, careful. This is the diameter, and the radius is 1/2 of this. Does that make sense? The radius is going to be 1/2 of what we have. It's going to be 1/2 of what we have. So hold on, let's go ahead and check it out. So if I was to plug in my area formula, 1/2 pi Oh, I was doing a different example in my head. I'm sorry, guys. I wasn't doing a semicircle. I'll show you an example where the 1/8 comes in handy. I wasn't doing a semicircle in my head. I apologize. 1/2 pi, and then what do I plug in? Yeah, doesn't r equal d over 2? So don't I need to go ahead and plug in 2 square root of 4 minus y squared all over 2? Okay. There we go. Lo siento. The 2's cancel, and then my squared, here's where it's going to be a little funny. My squared and my square root are going to cancel. So it'll just be 4 minus y squared. That's what would trip you up on this one with a semicircle. The 1/2 would stay the same, but in here the square root is no longer present. Now I'm going to dual page it and try to show you guys what I was trying to show with the 1/8, because a very common example that they use uses the 1/8. Let me see if this has a semicircle. Does it have a semicircle? No, it's square. No. Okay. So what if I was to give you something like, very similar in that I want semicircles, but let's do find the volume. Of the solid enclosed by y equals 2x minus 1 and y equals x squared, minus x minus plus 3. There you go. With semicircular cross sections perpendicular to the x-axis. Okay. Top minus bottom, great idea. Better find the natural bounds because they didn't give them to us. And it's not like a circle where it's self-enclosed. So we go over here and do our bounds of 2x minus 1. See if I made this right. If I moved everything to one side, 0 equals x squared minus 3x plus 4. Oh, I didn't make it right. Okay, pause. Make it minus 3 and plus 1. I know. I had the right values, I just did not get the right signs in there. I was having a little too much fun. Okay, now it'll work. Because now it'll be minus 4. So 0 is equal to x minus 1, nope, x plus 1, and x minus 4. So x is equal to negative 1 and 4. You guys agree? Okay, cool. So when we come over here, volume is equal to, since it's perpendicular to the x-axis, if I was to actually draw this, the thickness would be dx, which means I can just steal my negative 1 and 4 and plug those in. Now hold on, wait. What's my cross-sectional slice? And what's the area of a semicircle? So then question, why would the final answer on this one be 1/8 pi, the integral from negative 1 to 4 of x squared minus 3x minus 4 squared? I do need r squared, that's true, but where on earth did this 1/8 come from? Let's solve it. It's okay, let's solve it. Some of you go too quickly just picking an answer, but wait. Okay, so what's the process say? What do I need to put in here? 1/2 pi. Okay, who's squared? Who's my radius? The difference between, I like that, top minus bottom, difference between, where do I have the difference between shown somewhere? Right here, because I subtracted it all, right? Okay. Too many people would say done, but Charlotte just said, wait. 2. Why? If I was to draw this with my 2x plus 1, which would be something like this and something like this, I know that it intersects at negative 1 and 4. So if I was to make this negative 1-ish, plugging in negative 1, that's up a little bit. No, it's down a little bit. Something like that and that. Here are my two functions. If I was to take a slice perpendicular to the x-axis and pop up in a semicircle, this base which would be my top minus bottom, which I have x squared minus 3x minus 4. I'm going to put absolute value because actually we have it oriented wrong. The line should be on top. This base is going to be the diameter. So I need to go ahead and say radius is 1/2 of that. Now hold on. If I just said we oriented it wrong, why aren't there absolute values down here? It's going to be squared, so it's not going to make a difference. But if it was, say, a rectangular cross-section where I had base times height, there is no squared, I would need my absolute values, or I would need a picture to figure out who's the top and who's the bottom. Sarah? Oh, by subtracting 2x, and then by subtracting 1. So that was me setting the two equal to each other to find intersections or to find our natural bounds. And then just algebraically moving everything to one side. So ultimately it was top minus bottom, or actually in this case it was bottom minus top, because when you subtract it to the other side you end up combining all the like terms. Yeah. So we were doing the intersection, setting them equal to, but when you get one side equal to 0, you're doing top minus bottom, which is helpful. So does it make sense where the 1/8 comes from now? What's 1/2 squared? And what's 1/4 times 1/2? There's a 1/8 outside, not a 1/2. Tyler?
Is it just safe to assume that anytime you have like a semicircle like parts or whatever, that you have to half it? Because it will
Yes.
always be the diameter.
Yes. Anytime it's a semicircle, but a semicircle alone, because rectangles, squares, equilateral triangles, any sort of triangles, I need the whole base. Only with circles do I need it to take it in half. However, one more time, that's when we're dealing with semicircle cross sections. When we go into the next section, things are going to change just a little bit. Guys, it said that you're allowed to use a calculator on this one. There are decimal answers. Let's peek at it real fast. Calculator multiple choice, AP practice. If we'd had more time, this would have been our workspace this morning for AP practice on 6.2a. I want you guys to take a second. Feel free to talk about it in your groups. I'm going to give you literally a minute to read and try to set up an integral. Remember, you do not have to solve it by hand. You can solve it in your calculator. If you guys do get an integral, you can plug it into your calculator, yeah? And see if it matches with any of the ones up there. Now, just because it matches doesn't mean it's right. You could have made a common mistake. But maybe. You start playing. Charlotte, you yawn so loudly.
Show me the second curve. Go to the x-axis. No. I only saw the back. Because it's the x.
Good question. All right, so far, do you guys agree with my area that I'm building the third dimension off of? Because there's my ln of x, right? Here's my x equals e, cutting it. How do I know to stop there? Because it also says one more thing. Doesn't it also say and the x-axis? So it says take your ln, take your x equals e, take your x-axis. What's enclosed? Right there. If this was a fence and this was a fence and this was a fence, here's the pasture, right? That's what's inside. That's the field. Okay. Then it says cross sections perpendicular to the x-axis. So how am I going to do my slivers? Well, I already kind of did, didn't I? Aren't my slivers just going to go straight down to the x? Aren't they going to have little thicknesses of dx? And then what's popping up? A square. So I'm going to have squares popping up. Now, guys, do you have to draw these pictures every time? No, not even CalcChat does. But some of you, if you can draw it, it will help you visualize. Because when you look at the square, my top minus bottom down here, right? Isn't my base of my square going to be top minus bottom, so ln of x minus 0? What's on top? ln. What's on bottom? The axis. Oh, y equals 0. Which is the same thing as the side of my square. And why am I saying that? Because what's my volume formula need to be? From x1 to x2 of here it is. Sorry, I hadn't talked about it yet. Side squared is area. So therefore I'm going to do side squared. And my side is going to be ln of x minus 0, which is just ln of x. Now here's the struggle. Hold on, I still can't solve this yet until I figure out my bounds. My x2 is e, because that's as high as it goes. My ln of x minus 0 is just ln of x quantity squared. But the struggle is, what am I missing? So I said you guys are supposed to use your calculators. Who got me a decimal for the intersection of ln of x? You cannot use 0. ln of x does not even exist at 0, and it stops right there. Good. You could have used your calculator, or you could have just realized it's just going to be 1. Then you were supposed to plug and chug. If somebody hasn't yet, plug and chug it to the calculator, integrate. What do we got? If you're just putting this in your calculator, remember there's an E button on the calculator.
Just to find one.
Well, if you had graphed ln, you could have found the 1 by finding the 0. The E is given to you. So that's something you would have had to pull out of the problem. Does that make sense? They could have given you x equals 2 or 7 or 21, but they gave you E, so you just have to put the E in. All right, who has it?
0.718.
Okay. Whew. And we made all of ln of x squared, right? Okay. Kiddos, I have another example problem, but for right now, I do want us to introduce the next section, so give me just 1 second. I'm pulling up a demonstration, but as I do, you guys start taking 6.2b notes.
I don't think you could have got, because it's 2 if you do ln of quantity, or like x squared. And I don't think that was one of the answers. So.
Okay, good. Lucky for us.
Yeah, but I don't think that's the type of mistake.
You'd be surprised. Plugging stuff into calculators can be a struggle. if you guys notice as you're taking notes, what's different is that there's an area between that's being revolved first to make the three-dimensional volume. And this is kind of like pre-cal last year, how we had parabolas or hyperbolas or even lines that we spun. And that was to help you visualize this year. That wasn't the sole purpose, but that was a big part, at least as far as my motivation, was to help you visualize what this section entails. Because the last section, or I should say cross sections, you have an area that's like flat on a table and you're popping up in slices. You're popping up out of the region. This one, area that's established that's being spun. And as it's being spun, I mean, you can be thinking of a lathe and wood shop, you can be thinking of like glass blowing, you can be thinking of all sorts of different things as far as objects that are spun to be generated. But as this region is spun, a volume, a three-dimensional figure appears. Because spinning the second dimension generates the third dimension. And as you spin, maybe you guys can see that there are slices, because there truly are. As it's spun, maybe you guys can see there are slices. But because of the spinning, because of the revolution, solids of revolution, every time an object is spun, every time an area between curves is spun, you will always have a circular cross-section. But here's where it gets a little interesting. Unlike semicircular cross-sections, a solid with semicircular cross-sections, when you're dealing with solids of revolution, the top, that's not right. The top minus the bottom of the area is going to be your radius. The top minus bottom of your area is going to be your radius. This is why the AP likes to use semicircular cross-sections, because if you don't know what's going on, you could get very confused, because 1 second for solids of revolution, the top minus bottom is R. But the next second, like the cross-sections, the top minus bottom is D. It depends on how the solid's being generated. Is the solid being made by cross-sections coming straight up and restricted by the area? Or is the area being spun, and so the area itself is the radius? This leads us up to a formula that hopefully you'll get quite used to. These are the easiest types, discs. And the difference between disc and washer, let me turn off one of the lights if I can reach behind this Havana sign. The difference between discs and washers, discs are the are the easiest ones from this section, the solids of revolution, the volumes, because discs are flush with the axis. This is a solid figure. There is no way that you can like put your hand within. This is solidly formed. There are no gaps, no holes, no hollows. You can't put flowers in this. It's just one solid figure. That's a disc. And so the disc has a nice solid slice, and so we just say, no big deal, pi r squared. But instead of doing r divided by 2, we say, no, top minus bottom is r. It is halfway because that gets spun. So it's very, very, very similar to the cross-sectional idea, except because it's a revolution, automatically I know circles, automatically I know pi r squared. Not semicircles, it's the full circle formed by the revolution. And number 2, I know top minus bottom, or right minus left, will be the entire radius. Now guys, since it's chapel day, we're going to be a little bit behind, but here's what I want you guys to do. I'm going to go ahead and move this page of notes with washers to the very beginning. Because some of you, especially my artistic ones, you're going to want to take time making this right. And I think that's a really good thing to have ready for tomorrow. If you want to take pictures of it, you definitely can. I'll go ahead and dual page it. Or you can look online, and guys, I'm not kidding on this one. I'm going to give you 5 points just for having it. The spot check tomorrow will just be having your notes ready to go with these 2 pages, okay? If you want to take a picture of it, go ahead. My artistic ones, you might take a lot of time on it. My non-artistic, get the basics. But it will be a spot check if you have this updated in your notes tomorrow. Sound good? These 2 pages. Yeah. Well, to some degree. You can always print it out and put it in. That's okay too. Or you can just do, I mean, as you saw in CalcChat, the drawings aren't super necessary, but they do help in the visualization. All right, see you guys tomorrow. Homework. Get these 2 pages in your notes, and then we'll say discs and washers. Let's get really good at them.